These are the answers to the AP Chemistry packet on topics 6.6 to 6.9. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. In question 1, we are given a balanced chemical equation in which ammonia, or NH3, reacts with oxygen to produce carbon dioxide and water. And it says, it is observed that 13.0 kilojoules of energy is released when 1.00 grams of ammonia reacts completely with excess oxygen under standard conditions, according to the equation above. The value for the standard enthalpy change, or delta H, for the reaction represented by the equation above is closest to, and then we have 4 numerical choices. Let's focus on the units of these 4 choices, and the units are kilojoules per mole of reaction. So this question falls under topic 6.6, Introduction to Enthalpy of Reaction, and the essential knowledge statement says, the enthalpy change of a reaction gives the amount of heat energy released for negative values or absorbed for positive values by a chemical reaction at constant pressure. And in my video for topic 6.6, I mentioned the unit mole of reaction. And this unit, mole of reaction, is defined in terms of the specific set of coefficients for a particular chemical equation. And so because the unit of mole of reaction is connected to each coefficient in the balanced chemical equation, when we do the calculations here in question 1, we will need to consider that the coefficient for ammonia in the balanced equation is a 4. That's going to be part of our calculation. So again, we're looking for the unit kilojoules per mole of reaction. Let's start with the numbers that we are given in this question. So it says that there are 13.0 kilojoules of energy released for every 1.00 grams of ammonia. Now what I'm going to do is set up a conversion factor that will get rid of the units of grams of NH3 and convert into moles of NH3. So I'll calculate the molar mass of NH3 using the information on the periodic table. And so for the atomic masses of nitrogen and hydrogen, it's 14.01 for nitrogen, 1.008 for hydrogen times 3. And so the molar mass of NH3, or ammonia, is 17.034. Now at this point we can convert from grams to moles, but if we stop right now, in our calculation, the units of our final answer would be kilojoules per mole of NH3. But what we need to do is determine the kilojoules per mole of reaction. Again, we need the coefficient of 4 from the balanced chemical equation. So back in my video for topic 6.6, I was using this equation on this slide as an example, that there's 1 mole of reaction for every 2 moles of C4H10, or there's 1 mole of reaction for every 13 moles of O2, 1 mole of reaction for every 8 moles of CO2, 1 mole of reaction for every 10 moles of H2O. So back in question 1, we can see that because the coefficient of ammonia, or NH3, is 4, then there's 4 moles of ammonia for every 1 mole of reaction. So now if you look at the calculation, the grams of NH3 will cancel out, and the moles of NH3 will also cancel out, so that the units of our final answer will be kilojoules per mole of reaction. So if I pick up my calculator, it would be 13 times 17.034 times 4. And when I do that math, I get a value of 885.768, and that would be units of kilojoules of energy released for every 1 mole of reaction. Now, looking at the 4 answer choices, I can already eliminate choices B and C because the magnitude of the value is 221. And even though 884, which is featured in both choices A and D as a magnitude, is a little bit different than 885.768. It's close enough that we have narrowed down our answers to either A or D. Now we need to consider what should the sign of delta H for this reaction be. We do know that energy is released in this reaction, and in topic 6.6, we learned that when a reaction is exothermic and releases energy, the sign of delta H for that reaction will be negative. So this reaction is exothermic because energy is released, therefore the sign of delta H is negative, and the correct answer to question 1 is choice A. But if you're wondering about 884 versus 885.768, watch what happens if I use a slightly different value for the molar mass of ammonia, or NH3. If I change 17.034 to just simply 17, and if I multiply 13 times 17 times 4 on my calculator, I do get a value of 884. And again, the reason why the sign of delta H is negative is because this reaction is exothermic and energy is released. Again, the correct answer to question 1 is choice A. Now let's take a look at question 2. In question 2, we have a balanced chemical equation for the reaction between C2H2, which is acetylene, and oxygen, O2. It says a mixture of 3.0 moles of acetylene and 6.0 moles of oxygen are added to a previously evacuated reaction vessel. The mixture is sparked, initiating a chemical reaction according to the equation above. Which of the following identifies the limiting reactant and the amount of heat, or Q, released under standard conditions? So we first learned about the concept of a limiting reactant in Unit 4. It was topic 4.5, stoichiometry. The limiting reactant in a chemical reaction is the reactant that is completely consumed when the chemical reaction is completed and determines the maximum amount of product that can be produced, which is known as the theoretical yield. So in this question, we have 3 moles of acetylene and 6 moles of oxygen. And we can use the coefficients for acetylene and oxygen, which are 2 and 5, to convert from moles of acetylene into moles of oxygen. So I'll set up my conversion factor using those coefficients. There are 5 moles of oxygen consumed for every 2 moles of acetylene. And so 3 times 5 divided by 2 gives me a value of 17.5. 17.5 is the number of moles of oxygen that is needed to react completely with 3 moles of acetylene. But I only have 6 moles of oxygen available, so that makes oxygen the limiting reactant, because there is not enough oxygen available to react completely with 3 moles of acetylene. And if I do the other calculation, starting with 6 moles of oxygen, I can use those coefficients to convert from moles of oxygen to moles of acetylene. And when I do that, there's 2 moles of acetylene consumed for every 5 moles of oxygen. 6 times 2 divided by 5, I get a value of 2.4. So there's 2.4 moles of acetylene needed to react completely with 6 moles of oxygen. But I have 3 moles of acetylene available, and I only need 2.4 moles. So acetylene is the excess reactant because there is more than enough acetylene available to react completely with 6 moles of oxygen. So we have determined that oxygen is the limiting reactant and acetylene is the excess reactant. Let's look at our 4 choices. Because oxygen is the limiting reactant, we can eliminate choices A and B. And since the limiting reactant determines the maximum amount of product that can be produced, the limiting reactant is used to determine the amount of heat that is released in this experiment. So let's start with our quantity of oxygen, which is our limiting reactant. So we have 6 moles of oxygen. Let's also connect the unit of mole of reaction to the coefficient for oxygen in the balanced chemical equation. So we can see that the coefficient is 5. That means that for every 1 mole of reaction, 5 moles of oxygen is consumed. And then the delta H is given to us as negative 2,600 kilojoules per mole of reaction. So that means that because delta H is negative, this is an exothermic reaction in which heat is released, and there's 2,600 kilojoules of energy or heat released for every 1 mole of reaction. So now we can pick up our calculator and convert from moles of oxygen to mole of reaction, and from mole of reaction to kilojoules of heat released. So 6 divided by 5 times 2,600, we get a value of 3,120 kilojoules. So looking at our choices, we can eliminate choice C, and the correct answer is choice D, so that 3,100, when rounded off to 2 significant figures, that tells us the amount of heat that is released, and again, oxygen is the limiting reactant. Now let's take a look at question 3. In question 3, we're given a balanced chemical equation in which solid sodium reacts with liquid water to produce aqueous sodium hydroxide and hydrogen gas. We're also given the delta H for this reaction, which is negative 368 kilojoules per mole of reaction. In question 3, it says, when 2.30 grams of sodium is added to 200 milliliters of water at 25 degrees Celsius in a calorimeter, all of the sodium reacts with water as represented by the equation above. Which of the following is true when the 2.30 grams of sodium has completely reacted? And as we look through the 4 choices in this question, we can see that we'll have to decide between 18.4 kilojoules of energy or 36.8 kilojoules of energy. We also have to decide if energy is absorbed by the reaction or if energy is released by the reaction. Let's start with the quantity of sodium that we are given in this question. So we have 2.30 grams of sodium. So a good first step in this calculation would be, let's convert from grams of sodium into moles of sodium. And on the periodic table, we can see that the molar mass of sodium would be 22.99 grams. So now we've converted from grams of sodium into moles of sodium. The next step would be to connect the unit of 1 mole of reaction to the coefficient that is used in the balanced chemical equation for sodium. So because the coefficient for sodium is a 2, that means that for every 1 mole of reaction, there's 2 moles of sodium. And now the last step would be to get to kilojoules. So using the delta H, we can see that the units of delta H are kilojoules per mole of reaction, and the number is negative 368. So it's 368 kilojoules of energy for every 1 mole of reaction. We still have to decide if energy is absorbed or released. Well, let's go ahead and do the math so we can eliminate 2 of the 4 choices. So 2.30 divided by 22.99 divided by 2 times 368 gives us a value of 18.4 kilojoules of energy. Let's go ahead and eliminate choices B and D. And now, whether energy is absorbed or released has to do with the sign of delta H. So remember that when the sign of delta H is negative, that means that energy is released. It's an exothermic reaction. So because the sign of delta H is negative, this reaction is exothermic, energy is released. So the correct answer is choice C. 18.4 kilojoules of energy is released by the reaction. Now let's take a look at question 4. In question 4, we are given a balanced chemical equation in which aqueous HNO3, or nitric acid, is combined with aqueous KOH, or potassium hydroxide, to produce water and aqueous KNO3, or potassium nitrate. It says, in an experiment, a student mixes a 50 milliliter sample of 1 molar aqueous nitric acid with a 50 milliliter sample of 1 molar aqueous potassium hydroxide at 20 degrees Celsius in a coffee cup calorimeter. Which of the following is the enthalpy change of the reaction represented above if the final temperature of the mixture is 27 degrees Celsius? Assume that the total mass of the mixture is 100 grams and that the specific heat capacity of the mixture is 4.0 joules per gram degree Celsius. So for this question, it does involve calorimetry, which falls under topic 6.4, heat capacity and calorimetry. And we will use the equation Q equals mc delta T to calculate the amount of heat in this experiment. Let's start with Q equals mc delta T, in which the m represents the mass. So here the total mass of the mixture is 100 grams, and C represents the specific heat capacity of the mixture, which in this case is 4.0 joules per gram degree Celsius, and delta T is the change in temperature. So in this experiment, the temperature increased from 20 degrees Celsius to a final temperature of 27 degrees Celsius. That's a difference of 7 degrees Celsius. So if I pick up my calculator and do 100 times 4 times 7, I get 2,800, and the units would be joules. Now, if I want to convert 2,800 joules into units of kilojoules, remember that 1 kilojoule is equal to 1,000 joules. So I could take 2,800, divide by 1,000, and I would get 2.8 kilojoules. Now, at this point, with an answer of 2.8 kilojoules, choices B and C might be attractive at this point, but look at the units for all 4 of these choices. The units are not just kilojoules. The units are kilojoules per mole of reaction. So what we still need to do to calculate the correct answer in this question is to connect the 2.8 kilojoules to this quantity of mole of reaction. Now we are given the volume and the molarity for nitric acid. So it's 50 milliliters of a 1 molar solution, and we are also given that there are 50 milliliters of a 1 molar solution of potassium hydroxide. So what that means is that the moles of HNO3, or nitric acid, is the same as the number of moles of KOH, or potassium hydroxide. So we don't have an issue with a limiting reactant and an excess reactant. The number of moles of each reactant are the same. That means that we can focus on calculating the number of moles of either nitric acid or potassium hydroxide, and then we can connect that to the coefficients in the balanced equation to calculate the quantity mole of reaction. So I'm going to start with the nitric acid because that's the first chemical listed in this question. So we have 50 milliliters. First, I'm going to convert from units of milliliters into liters. So I will do the conversion factor that has 1 liter for every 1,000 milliliters. And then 1.0 moles per liter, that's my next conversion factor. So I've converted from milliliters to liters, and now from liters of solution to moles of nitric acid. Well, since the coefficient for all of these substances is 1, I can look at the coefficient of 1 and realize that for every 1 mole of reaction, there's 1 mole of nitric acid. So now I can convert from milliliters to liters, from liters to moles of nitric acid, and then finally from moles of nitric acid to mole of reaction. So the math here will be 50 divided by 1,000, and then everything else is 1. So 50 divided by 1,000 is 0.050 mole of reaction. Let's connect the 2.8 kilojoules to 0.050 mole of reaction. And so that ratio, 2.8 divided by 0.05, gives me a value of 56 kilojoules per mole of reaction. Now, I haven't said whether this is going to be a positive or a negative number for the enthalpy change, but we can tell that the correct answer is either A or D. Let's go ahead and eliminate choices B and C. And so to determine whether this reaction should be classified as endothermic or exothermic, let's look at what happened to the temperature change in this experiment. So in my earlier video for topics 6.1 to 6.5, I said that if a temperature change occurs during the process of forming a solution or during a chemical reaction, it is important to understand the direction of heat flow between the system and the surroundings. Note that the thermometer is usually considered to be part of the surroundings and not the system. So during a chemical reaction, if the temperature increases when two chemicals are combined together in a calorimeter, then heat is flowing from the system into the surroundings. So it should be an exothermic reaction. So we know that in this experiment, the temperature increased from 20 degrees Celsius to 27 degrees Celsius. Therefore, the temperature increases as this reaction proceeds. This reaction is exothermic, and the sign of delta H is negative. So the correct answer to question 4 is choice A. The enthalpy change for this reaction is negative 56 kilojoules per mole of reaction. Now let's take a look at question 5. In question 5, it says, a student sets up 2 experiments in which samples of C4H10, which is butane, and C2H5OH, which is ethanol, are combusted in separate calorimeters. Each combustion reaction occurs in the presence of excess oxygen and goes to completion according to the chemical equations shown in the table above. Information about the experiments is shown below. What mass of ethanol should be used in experiment 2 in order to release the same quantity of heat, Q, that is released in the combustion of 25.0 grams of butane in experiment 1? So to begin this problem, let's calculate the amount of heat released from the combustion of 25.0 grams of butane in experiment 1. So we'll start with 25.0 grams of C4H10, and then based on the information from the periodic table, as well as the molar mass that's given in this question, there are 58.12 grams of butane for every 1 mole. So now that we've converted from grams of butane into moles of butane, let's look at the coefficient for butane in the combustion reaction. So in the equation, there is a coefficient of 1 for the butane. That means that for every 1 mole of reaction, 1 mole of butane is consumed. Now, the delta H is negative 2,880 kilojoules per mole of reaction. So that means that 2,880 kilojoules of heat is released for every 1 mole of reaction. Now that we've converted from grams of butane to moles of butane, from moles of butane to mole of reaction, and then finally from mole of reaction to kilojoules, we can pick up our calculator, and it's going to be 25 divided by 58.12, and then times 2,880, and our answer will be in units of kilojoules. So I get 1,239 kilojoules of heat released in experiment 1. Let's start with that number and do the calculations for experiment 2. So with experiment 2, now we have ethanol and we have the other chemical equation for the combustion reaction. So 1,239 kilojoules. Now we're going to convert from kilojoules to units of mole of reaction. So the delta H for the combustion of ethanol, it's negative 1,370 kilojoules per mole of reaction. So for every 1 mole of reaction, that's 1,370 kilojoules. Now, because there's a coefficient of 1 in that equation, for every 1 mole of ethanol, there's 1 mole of reaction. And then finally, using the information from the periodic table to get the molar mass, there's 46.07 grams of ethanol for every 1 mole of ethanol. So we can pick up our calculator, and then the answer will be in units of grams of ethanol. So 1,239 divided by 1,370 and then times 46.07. And if we do that math, we get an answer of 41.7 grams of ethanol consumed in experiment 2 to give the same amount of heat that was released in experiment 1. So the correct answer to question 5 is 41.7, which is choice C. Now let's take a look at question 6. In question 6, it says the structural formula of acetylene, C2H2, is shown above. Acetylene gas reacts with hydrogen gas to form ethane gas, which is C2H6, as represented by the following equation. We are given a table with bond energy data for various bonds, and question 6 says, based on the table of bond energies shown above, the value of delta H, or the change in enthalpy, for the reaction C2H2 plus 2H2 to produce C2H6 is closest to which of the following? And we see 4 numerical answers. Again, all of the units are kilojoules per mole of reaction. So this question falls under topic 6.7, bond enthalpies. During a chemical reaction, bonds are broken and or formed, and these events change the potential energy of the system. And if you are given a data table with bond energy values and you need to calculate the delta H for a particular chemical reaction, this is the equation that you use to do that. So bond energy data can be used to calculate the value of the change in enthalpy, or delta H, for a chemical reaction. The equation is delta H for the reaction is equal to the sum of the bond enthalpies of the bonds that are broken, because breaking bonds is an endothermic process, minus the sum of the bond enthalpies of the bonds formed, because forming bonds is an exothermic process. So we're going to use that equation to answer question 6. Now let's focus on the reactant side of the equation. So on the reactant side of this equation, we have 1 mole of acetylene, C2H2, and we have 2 moles of hydrogen, H2. So now let's make a list of all of the bonds that are broken in this reaction. So looking at the structural formula of acetylene, we can see that as far as bonds broken, that would be 2 carbon-hydrogen single bonds, 1 carbon-carbon triple bond, and then since there's a coefficient of 2 in front of the hydrogen, that means that there will be 2 hydrogen-hydrogen bonds that are broken. So that is our list of the bonds broken. Now on the other side of the equation, we have C2H6, and the structural formula of C2H6 looks like this. And the bonds that are going to be formed in this reaction would be 6 carbon-hydrogen bonds and 1 carbon-carbon single bond. Now that we've made the list of all of the bonds that are broken and all of the bonds that are formed, let's use the numbers for bond energy from the table to do that calculation. So the delta H will equal the sum of the bond enthalpies of the bonds broken. Let's start with that. So carbon-hydrogen has a value of 413 kilojoules per mole. So we have 2 of them, so 2 times 413. And then we have that carbon-carbon triple bond, which has a value of 839 kilojoules per mole. So let's add 839 to our total. And then there are 2 hydrogen-hydrogen bonds, which have a value of 432 kilojoules per mole. So it's going to be 2 times 432. So that will be the sum of all of the bond enthalpies of the bonds broken. Now, for the sum of the bond enthalpies of the bonds formed, we have 6 carbon-hydrogen bonds, so 6 times 413. And then we have 1 carbon-carbon single bond that is formed, and that's 347. So now that all the numbers are in place in this equation, we can pick up our calculator and do the math. So 2 times 413 plus 839 plus 2 times 432, and that's a total of 2,529, and then minus 6 times 413 plus 347, so that total of bond enthalpies of bonds formed is 2,825. So 2,529 minus 2,825 is our answer, and it works out to be negative 296, and the units for delta H are kilojoules per mole of reaction. So based on that result, the correct answer to question 6 is choice B. The change in enthalpy for bonds broken minus bonds formed gives us a value of negative 296 kilojoules per mole of reaction. Now let's take a look at question 7. In question 7, it says, which of the following best explains why the sign of delta H for the reaction represented above is positive? So just like in question 6, here in question 7 we have to consider the following equation in which bond energy data can be used to calculate the value of delta H. So in that equation, the delta H for a reaction is equal to the sum of the bond enthalpies of bonds broken minus the sum of the bond enthalpies of bonds formed. Now, unlike in question 6 where we actually had to do a calculation, here in question 7 we are not given a table of bond energies. So question 7 is more of a conceptual understanding of this equation. So breaking bonds is an endothermic process in which energy is absorbed. Forming bonds is an exothermic process in which energy is released. Let's read the 4 choices in question 7 carefully and see if we can find an incorrect statement that will allow us to narrow down the choices. So I'll start with the first few words in choice A. In choice A, it says the energy absorbed as the bonds in the reactant are broken. Well, that part is correct because breaking bonds is an endothermic process. And now moving on to choice B, it says the energy released as the bonds in the reactant are broken. So that's definitely incorrect. Breaking a bond is an endothermic process. Energy is not released. We can eliminate choice B, and if we look down in choice D, it's that same incorrect statement. It says the energy released as the bonds in the reactant are broken, so that's incorrect. Let's go ahead and eliminate choices B and D. Now, comparing choices A and C, the only major difference is one says greater than, and then the other says less than. So here we have a delta H for this reaction, which is positive. That means that if delta H is positive, the sum of the bond enthalpies of bonds broken must be a larger number, and the sum of the bond enthalpies of the bonds formed must be a smaller number. Now let's read choice A all the way through. It says the energy absorbed as the bonds in the reactant are broken is greater than the energy released as the bonds in the product are formed. So that's exactly correct because it should require more energy to break the bonds and less energy is released when the bonds are formed. So choice A is the correct answer to question 7. Now let's take a look at question 8. In question 8, it says ethylene, C2H4, reacts with chlorine, Cl2, to produce 1,2-dichloroethane, C2H4Cl2, as represented by the equation shown above. We are given a table with bond enthalpy data, and it says a student performed the following calculation using the bond enthalpy values in the table above to estimate the value of delta H for the formation of 1,2-dichloroethane. So we see the student's calculation, and then question 8 asks, what error did the student make in the setup for this calculation? So our strategy for answering question 8 is to go ahead and solve the problem correctly, and then hopefully after we solve the problem correctly, we can find out what mistake the student made. So it's going to be bonds broken minus bonds formed. Let's start with the ethylene and the chlorine. Now, the Lewis diagram for chlorine is going to be a chlorine-chlorine single bond, and we can see that that is one of the bonds listed in the bond enthalpy table. So here are all the bonds broken in this reaction. So we can see in the ethylene structural formula, that would be a carbon-carbon double bond that is broken. And then we can see 4 CH bonds in ethylene. So those are also broken. In addition, we have the chlorine-chlorine bond that is broken. So that is the total of all of the bonds that are broken. Now let's look at the other side of the equation. So here's the structural formula for 1,2-dichloroethane. And the bonds that are formed would be the following. A carbon-carbon single bond, 4 carbon-hydrogen bonds, and 2 carbon-chlorine bonds. So that is the list of the bonds formed. Now that we have a list of the bonds broken and the bonds formed, let's use the data in the bond enthalpy table to do the math. Let's go ahead and set up our equation with the sum of the bond enthalpies of bonds broken, and that would be a carbon-carbon double bond, which has a value of 614 kilojoules per mole, so 614. We have the carbon-hydrogen bond, which comes in at a value of 413 kilojoules per mole, and we have 4 of them, so 4 times 413. And then we have that chlorine-chlorine bond, which has a value of 243 kilojoules per mole. So we'll add 243 to the total. So that is the sum of the bond enthalpies of bonds broken. Now let's move on to the bonds formed. There should be a carbon-carbon single bond, which in the table has a value of 347 kilojoules per mole, so 347. And then we have carbon-hydrogen bond at 413, and we have 4 of them, so 4 times 413. And then the carbon-chlorine bond has a value of 339 kilojoules per mole, and we have 2 of them, so 2 times 339. Now let's pick up our calculator and do the math. So 614 plus 4 times 413 plus 243. And that gives us a total of 2,509. And then for the bonds formed, it would be 347 plus 4 times 413 plus 2 times 339, and we get a value of 2,677. So 2,509 minus 2,677 gives us an answer of negative 168 with the unit of kilojoules per mole of reaction. If we compare the correct answer that we just got to the student's error looking for a mistake, we can see that the only mistake the student made was to reverse the sign. So they used all of the correct numbers for the bonds, but they got a value of positive 168, which means there was a reversal in their setup. Now, this equation, which is in topic 6.8, and we're going to see that used later on in this packet, but that equation of products minus reactants is on the equation sheet, but this equation, the bonds broken minus bonds formed, is not on the AP Chemistry equations and constant sheet. So it is possible that the student set up their reaction or set up their calculation backwards by doing products minus reactants. So as far as the correct answer to question 8, what error did the student make in the setup for this calculation? Because they got it backwards, then the student assumed that energy is released when bonds are broken. In other words, they put the bonds broken in front of that minus sign. They have it backwards, so they assumed that breaking a bond would release energy and that forming a bond would absorb energy. Because they got it backwards, that's why the sign is positive 168 instead of negative 168. So the correct answer to question 8 is choice D. The student assumed that the energy is released when bonds are broken. Now let's take a look at question 9. In question 9, we are given a data table. And in this data table, it says standard enthalpy of formation for 3 different substances: oxygen, or O2, sulfur dioxide, or SO2, and sulfur trioxide, SO3. So question 9 says, based on the information in the table above, which of the following choices is closest to the value of delta H for the reaction represented by the following equation? Now let's compare the data table here in question 9 with the data table that you were given in the previous question, question 8. Notice that bond enthalpy data is different than the data for standard enthalpy of formation. So because the data is different, that means that the equation that we're going to use to solve this question is going to be different. So we're not going to use bonds broken minus bonds formed. In fact, question 9 falls under topic 6.8, enthalpy of formation, and the essential knowledge statement says, tables of standard enthalpies of formation can be used to calculate the standard enthalpies of reactions. So we're going to use the sum of the standard enthalpy of formation for the products minus the sum of the standard enthalpy of formation for the reactants. So let's go ahead and take a look at that equation, and the reaction that we have involves 2SO2 plus O2 for the reactants and 2SO3 for the products. So we'll start with the products. Now SO3, sulfur trioxide, has a value for its standard enthalpy of formation of negative 395.7 kilojoules per mole. But because there is a coefficient of 2 in this equation, we have to take that number and multiply by 2. So it's going to be 2 times negative 395.7, and that takes care of the products. Now let's move on to the reactants. So for the reactants, we have 2SO2 plus O2. So the value for sulfur dioxide, or SO2, is negative 296.8. I also see a coefficient of 2 for the SO2, so we're going to multiply that number by 2. And then by definition, the standard enthalpy of formation for an element in its standard state would be 0, so oxygen has a value of 0. So here is the math that we're doing. 2 times negative 395.7 minus 2 times negative 296.8. So when I pick up my calculator, I get negative 791.4 minus negative 593.6. And so my answer on my calculator is negative 197.8, and the units would be kilojoules per mole of reaction. So now that we know that the value of delta H for this reaction is equal to negative 197.8 kilojoules per mole, that means that the correct answer to question 9 is choice A. Now, let's take a look at question 10. In question 10, it says, the combustion of acetaldehyde, CH3CHO, occurs according to the equation above. Based on the information in the table below, and the value of the standard enthalpy change for the combustion of acetaldehyde, which of the following is closest to the value of the standard enthalpy of formation for acetaldehyde? So in the table below, there are 4 different substances listed. There's acetaldehyde, which we don't know the value for the standard enthalpy of formation, so that's what we're trying to find. And then we have oxygen, O2, which has a standard enthalpy of formation of 0. And then we have carbon dioxide gas, which has a value for the standard enthalpy of formation of negative 394 kilojoules per mole. And then we have liquid water, which has a standard enthalpy of formation of negative 286 kilojoules per mole. So we're going to use the same equation in question 10 that we used in question 9. And in question 10, we already know the value for the enthalpy change for the overall combustion reaction. So that is listed to the right of that balanced equation. So that delta H is negative 2,390 kilojoules per mole of reaction. So I'm going to put that on the left side of the equation. That's negative 2,390. Now let's take a look at the products. So the products would be 4 moles of carbon dioxide gas and 4 moles of liquid water. So the number for carbon dioxide would be negative 394 kilojoules per mole, Let's multiply that by 4 because we have a coefficient of 4. And then for water, it's going to be negative 286 kilojoules per mole. Again, because of the coefficient of 4, we'll multiply by 4. So now we have our information for all of the enthalpy of formation for the products, the CO2 and the H2O. Moving over to the reactants, we have 2 moles of acetaldehyde, but that's the question mark in the table. So we don't know that value. But we do know that for oxygen it's going to be 0. So on the reactant side, we have 2 times a unknown quantity, which we're trying to solve, plus 5 times 0. So now I'm going to go ahead and take care of the math. So 4 times negative 394 plus 4 times negative 286 gives me a value of negative 2,720. But for the reactants, I just have 2 times an unknown quantity, so I'm calling that 2x. So negative 2,390 is equal to negative 2,720 minus 2x. Now this just becomes an algebra problem where we have to solve for x. So I get 2x equals negative 330 when I rearrange that equation and do some algebra and do some math. So if 2x equals negative 330, that means that x, which is what I'm trying to find, the standard enthalpy of formation for acetaldehyde, is negative 330 divided by 2. And that works out to be negative 165 kilojoules per mole. So now that we have answered that question, we take a look at our 4 choices, and the correct answer to question 10 is choice B. The standard enthalpy of formation for acetaldehyde is negative 165 kilojoules per mole. Now let's take a look at question 11. In question 11, we are given a data table with 3 different chemical equations, and for each equation there is a value of delta H listed. Question 11 says, based on the information in the table above, what is the value of delta H for the following reaction? So we have a reaction in which 2 moles of H2O2 react with 1 mole of N2H4 to produce 4 moles of H2O plus 1 mole of N2. Now, question 11 falls under topic 6.9, which is Hess's law. And so with Hess's law, there are various modifications that you can make to a chemical equation, such as reversing the equation, or multiplying all of the coefficients by a particular constant, or adding equations together, and then whatever you do to the equations, you can see how delta H is affected by those modifications. Let's go ahead and take a look at what we need to do to these 3 chemical equations, if anything, so that when we add them together, they will equal the equation that I'm highlighting with that red box on the slide. Now, the first substance I'm going to focus on is the substance H2O2. So what I need is 2 moles of H2O2 to appear on the reactant side, or the left side of the equation. When I look at the data table, I can see that there already is a chemical equation that has 2 moles of H2O2 on the left side of the equation. So therefore, no changes need to be made to that equation at all. All I'm going to do is rewrite that equation exactly as it is. And the delta H for that equation is negative 196 kilojoules per mole of reaction. Now, the next substance I'm going to focus on is N2H4. So what I need is 1 mole of N2H4 to appear on the left side of the equation. When I look at the data table, I can see that this chemical equation has 1 mole of N2H4, but it's actually on the right side of the equation. And I need that N2H4 to be on the left side of the equation. So what that means is that that equation needs to be reversed. And according to Hess's law, if the equation is reversed, then the sign of delta H for that reaction is reversed. So that means that instead of having a delta H of positive 51, the delta H will be negative 51 when I reverse that equation. So you can see I've rewritten the equation with N2H4 on the left, and then 1 mole of N2 and 2 moles of H2 on the right, and I changed the sign of delta H when I did that reversal. Now you'll notice that hydrogen does not appear in that chemical equation inside that red box. So I need to get 2 moles of hydrogen to cancel out so it does not appear in the overall chemical equation. So I find hydrogen in this particular equation in the data table. Now it is 1 mole of hydrogen on the left, but I need there to be 2 moles of hydrogen on the left so that when those equations are added together, the hydrogen will cancel out. So what that means is I'm going to take that particular equation from the data table and multiply all of the coefficients by 2. According to Hess's law, if an equation is multiplied by a particular constant n, then the value of delta H for the reaction is also multiplied by that same constant n. So as you can see, I'm taking the original equation and I'm multiplying each of the coefficients by 2. So now the coefficients are 2, 1, and 2, but the delta H is no longer negative 286. Now the delta H is equal to negative 572 because I multiplied that delta H by 2. At this point, I'm ready to check and see if it's going to work. I'm ready to add these 3 equations together. And according to what Hess's law says, if 2 or more equations are added together to produce a new overall equation, the values of delta H from each equation are also added together to determine the value of delta H for the overall equation, the new equation. Let me go ahead and see if I can cross off any chemicals that appear on opposite sides for these equations. So I see oxygen on the right, oxygen on the left, so I'm going to cross those out. I see 2 moles of hydrogen on the right and 2 moles of hydrogen on the left, so I can cross those off. And now the overall equation has 2 moles of H2O2, 1 mole of N2H4, a total of 4 moles of water, and 1 mole of N2. So now that procedure is successful. So what's the delta H for the overall new equation? It's going to be negative 196 plus negative 51 plus negative 572. And so when I do that math, I get a value of negative 819, and my units are kilojoules per mole of reaction. So now that I know the correct answer to this question, let's go ahead and take a look at the 4 choices in question 11. So because the overall delta H is equal to negative 819 kilojoules per mole of reaction, the correct answer to question 11 is choice A. So question 11 is the last question in this packet. I hope that you found all these answers and explanations helpful. Thanks for watching.